Let us talk about significance and multiple testing. So I will have two parts to this presentation. We will first speak about significance, and I will introduce a number of definitions, and then also I will introduce the score test once again, and we will talk about significance of the score test statistics. And then we will start considering the problem of multiple testing, and I will show you a few examples, and we will figure out one of the ways to deal with the problem of multiple testing. So one of the important things which I want to tell during this presentation, the message I would like to convey, is distinction between p-value and type 1 error. So let's start with significance and with some definitions. So let's define an experiment as a planned connection, a planned process of data collection. So any planned process of data collection could be called an experiment. But what is the critical word here is the planned process. And let's consider a very simple experiment where we measure some outcome y and predictor x in a set of people, and if we put this in medical context, outcome y could be some disease, for example type 2 diabetes, and predictor x could be some risk factor. So for type 2 diabetes, classical risk factors to consider would be obesity, unhealthy lifestyle, so on and so forth. So we consider a very simple experiment, outcome and some predictor or risk factor. So we define the null hypothesis as a hypothesis of no association between the outcome and the predictor. So we do the experiment, we do planned collection of some data, and this data can be characterized by test statistics, which measures how much the data deviate from the expectation under the null hypothesis of no association. And you could think of many test statistics in general. This could be actually any value which would measure deviation from the expectation under the null. But we will consider again the score test, t-squared defined as the coefficient of determination, which is correlation squared multiplied by sample size. So again, the coefficient of correlation measures the association, how strong is the relation between the outcome and the predictor, and then the more is the sample size, the stronger is the evidence that this deviation from the null hypothesis is not because of random stochastic causes. So we will use the score test. The p-value is defined as the probability to obtain the value of the test statistic at least as big as the observed one if the null hypothesis is true. Usually the test statistic is chosen that it comes from a known probability distribution. For example, the score test is coming from the chi-square distribution, so we know this distribution, and then for certain values of the score statistics we also know corresponding probabilities that these test statistics will be this big or even larger. Well, again, if your t-square is 3.84, we know that 5% of probability distribution, chi-square distribution with 1 degree of freedom, will be after this point. So that's the exact definition of the p-value. So let's continue with a few more definitions, and in an experiment we will reject a null hypothesis of no association if the test statistic is greater or equal to some predefined threshold, which is termed critical value at which we reject the null hypothesis. And type 1 error is an event an event which occurs in experiment when we reject the null hypothesis, so we get test statistics greater than critical value, while it is true, right? So if in experiment we obtain the test statistic over critical value and reject null hypothesis while actually there is no association there, null hypothesis is true, we call this an event of occurrence of type 1 error. The p-value, as you remember, is related to the probability that a test statistic has value as obtained in the experiment or greater. So it's the cumulative distribution of some, its cumulative probability distribution after some point, right? But if we consider some very simple experiment in which we measure a single test statistic, and this test statistic is good one, we can interpret the p-value as the probability that in this experiment the null hypothesis is rejected while it is true. Thus, the smaller is the p-value, the greater is our confidence that the null hypothesis is not true. If such simple experiment is repeated and the test statistic is proper, then type 1 error rate, so the frequency of rejection of null hypothesis while it is true, should converge to the p-value. So let's consider what type of critical value we are going to use. So the score test is known to be distributed as chi-square with 1 degree of freedom when null hypothesis is true, as I have already demonstrated several times. We know that for the chi-square distribution with 1 degree of freedom, 5% probability distribution is behind the point of 3.84. So let's use this 3.84 as a critical value. In case we obtain the score test statistic value more than 3.84, we are going to reject the null hypothesis and claim that there is a true association in the data gathered in this experiment. Now think that if we will repeat this experiment over and over again, then the type 1 error rate, so the proportion of times in these multiple experiments we are going to reject null hypothesis, should converge to the p-value, should converge to the 5%. So next we are going to check this. So I designed the following Monte Carlo experiments. I'm simulating a phenotype for 100 people totally at random. I just take that as a realization from a normal distribution, and totally independently from this phenotype I simulate a genotype, right? Under assumption of Heidenreich, that would be a realization from binomial distribution. So the null hypothesis perfectly holds in my simulated data, and then I simulate one data set, and then the second data set, and then the third data set, and so on. And for each data set, for each simulation experiment, I'm estimating the coefficient of correlation, compute the coefficient of determination, and then of course I can easily compute the score test value, which will be my sample size by coefficient of determination, so 100 times the estimate of coefficient determination obtained in this particular simulation experiment. So I'm going to record for each experiment, I'm going to record the t-square value and repeat procedure many times. At the end I'm going to have a vector of these test statistics, and then in these repeated experiments we assume the critical value of 3.84. So as soon as in any experiment we obtain the t-square more than 3.84, this is type 1 error event, and type 1 error rate would be the proportion of these t-squares over 3.84. And we're going to check if this error rate would converge to the p-value, and we know that for the score test with critical threshold of 3.84, 5% of distribution is behind that point, so p-value is 5%. Okay, here I show the data which I obtained in my first 4 simulation experiments, and on the first panel, so each dot represents a sampled individual, and I have 100 such dots in any of these plots. So for example, this dot corresponds to an individual who has genotype coded as 0, so it's AA, AB, BB. So this guy is AA, and this simulated sample has a rather high value of the simulated phenotype of about 2. So I have 100 of these dots, and then I test if there is a linear association between the genotype and the phenotype. I compute the coefficient of correlation, and in this data set it is 0.019, so it's really small. But again, in my simulations I assume null hypothesis, so there is no association there. Any association I would see would be type 1 error. And with this coefficient of correlation, I square it, multiply it by 100, I get the score test value of 0.035, which is smaller than 3.84, so I do not reject the null hypothesis for this experiment. For the second experiment, the same. For the third experiment again, I do see kind of trend, but statistically it's quite weak, and my score test is 1.2, so it's still less than 3.84. However, in the fourth experiment, you see, just by random chance, I do obtain a significant trend between the genotypes and phenotypes. So the coefficient of correlation in this data is 0.2, and if I square it and I multiply it by 100, I get the score test value of 4, and here I reject the null hypothesis, so in this data set I have occurrence of type 1 error. So I'm repeating these experiments over and over again, and I present them using the following graph. So here on x-axis I have the index of the experiment, so I start with experiment 1, 2, 3, 4, 5 and so on, and on y-axis I write down type 1 error, so that's the number of t-squares which are more than 3.84 divided by the current number of experiments. So you can see that you remember during first 3 experiments I did not reject a null hypothesis, so my type 1 error was 0, and you can see 3 dots here. And then in experiment number 4 I had the occurrence of type 1 error. We obtained the test statistics of 4, and then 1 out of 4 type 1 error becomes 25%. And then in the following experiments null hypothesis is not rejected, so type 1 error becomes smaller, and then around 19th experiment I have another occurrence of type 1 error, and so on and so forth. If I repeat my experiments many times, then I can clearly see that type 1 error does converge to a certain value, and this value is actually 5%. This is my p-value. So this is very nice result. We show that if we do a very simple experiment where we do a single test, compute this single test statistics, then the p-value of this test statistics corresponds to the experimental type 1 error. Let us consider a little bit more complex experiments. So in previous experiments, we were collecting the data on single outcome and single SNP, and we would test the association between the SNP and the outcome. Now let's consider we are doing some candidate gene study and we measure not two SNPs, but we measure not one SNP, but we measure two SNPs. And for each of them, we do compute the test statistics. And we are going to claim that we do detect significant association with our candidate region. We are going to reject the null hypothesis if we observe the test statistics more than 3.84 for either of the two SNPs. So if we get it for one of the two SNPs, we say there is association. If we get it for both SNPs, we also say there is association, right? So p-value is still 5% because the probability that score test will have value more than 3.84, the probability over chi-square distribution would be still 5%. But what will be the type 1 error in this scenario? So we are going to check this in a very similar manner as we did the check between type 1 error and p-value before. So here, again, there are 4 panels, but these are results from 2 experiments. So in each experiment, I'm testing association with 2 SNPs. Again, all these data are random, and the phenotypes I simulate once, but the genotypes for 2 SNPs I simulate twice, and in the model there is no association between these values, so it's pure null hypothesis model. So here are the results from my first simulation experiment, and then for the first SNP I obtained coefficient of correlation between the SNP and the phenotype of 0.087, which gives me the score test of 0.75, and for the second SNP I have score test of 2.2. So both of them are less than 3.84, so in this experiment I'm not rejecting the null hypothesis. Now this is my second experiment, and again for both SNPs the value of the test statistic is less than 3.84, so I do not reject the null hypothesis. If I would see t-square of more than 3.84 for any of these SNPs, of any of these 2 SNPs, I would reject the null hypothesis. So let's see what happens when I repeat my experiments over and over again, and then you can see that again in the first 2 experiments I didn't have type 1 error event, but apparently in the third experiment I rejected the null hypothesis, so type 1 error became 1 over 3, so roughly 0.33. And then the following 1, 2, 3 experiments I did not reject the null hypothesis, and then I rejected it again. And all this is pure type 1 error. So if I repeat experiments over and over again, I see that type 1 error does converge to some value, but actually this value is not the p-value, not the 5% p-value which is depicted by the green line, but some other value. Can somebody tell me what exactly this value is, or maybe not exactly, but a bit roughly? So the type 1 error in this experiment is roughly 10%, or to be more exact, this is 9.75%. Okay, now I scale up my experiments, and this is not very uncommon for a candidate region to test a large number of SNPs, and I'm considering an experiment where I test 10 SNPs for association with my outcome of interest, and I would reject a null hypothesis if I see the scored test more than 3.84 for any of these SNPs. So my p-value is still, my nominal p-value is still 5%, right? Now you can see that the type 1 error in this experiment will be rather high. It actually would converge to a value which is around 40%. So in 40% of my experiments, I do reject null hypothesis while it is true, and this is not really acceptable. So what I want, effectively, to keep under the control is not p-value, because p-value is characteristic of chi-square distribution. I really want to keep my type 1 error to 5%, so I know what is the probability that I claim association, but actually it's not true. So from these experiments we can clearly see that when you are doing multiple testing within the same experiment-wise type 1 error is not the same as the p-value which you use for the single test. When experiments consisted of 2 tests, then p-value of 5% for single test corresponded to experiment-wise type 1 error of roughly 10%, and with testing 10 SNPs in single experiment, this procedure corresponded to type 1 error of 40%. The experiment type 1 error can be rather easily estimated from critical p-value level used to do rejection of the null hypothesis and the number of tests in the experiment. From very basic probability theory, we know how to compute the probability of union events. So what we are interested in is the probability that the test statistic from test 1 is greater than or equal to 3.84, or test statistic from the test 2 is greater than or equal to 3.84. So what's the probability of such an event? And if we assume that 2 tests are independent, this is rather easy to compute. So this would be a probability that event happens in test 1 but doesn't happen in test 2, plus the probability that the event does not happen in test 1 but happens in test 2, plus the probability that event happens in both tests. But this probability that event happens, probability that test is more than 3.84, this is exactly our p-value. And then the probability that the event does not happen, so the test is less than 3.84, this is 1 minus our p-value, right? So while the p-value is the proportion of the distribution on the right after the critical point, the probability that the test statistic is less is 1 minus that proportion of distribution before this critical value. So then we can compute the probability that we would obtain test statistic more than 3.84 in either of the 2 independent experiments by multiplying these p-values and adding them up, and if we do so, we would obtain the value of 0.0978, 9.75%. So this is exactly what you expect according to probability theory, the type 1 error in an experiment which consists of 2 independent tests and we reject null hypothesis when either of these tests shows p-value less than or equal to 5%. Keeping this in mind, we can actually figure out what the nominal p-value should be so that type 1 error is acceptable. Because again, we are not interested in nominal p-value for single test. We are interested that in our whole experiment we keep type 1 error under control. And usually the desired type 1 error rate should be 5%. But if we look at these formulas, it's relatively easy to modify the critical p-value, critical threshold, and consequently critical p-value, so that the type 1 error is not 10% like here, but would be 5%. And it appears if for this experiment with two independent tests, we would use 2.5% as the critical p-value at which we tell, yes, we are going to reject a null hypothesis. This would correspond to type 1 error of 5%. So this type of reasoning leads to the Bonferroni correction, and this Bonferroni correction procedure says that in an experiment including an independent test, if you want to keep experiment-wise type 1 error rate of alpha, then the critical p-value you should choose according to this formula, alpha divided by the number of these independent tests you are doing in your experiment. And then your type 1 error would stay at predefined level of alpha, and usually you want this alpha to be 5%. So for experiment consisting of doing two tests, your p critical should be 5% divided by 2, 2.5, and then if you would be doing 10 tests in your experiment, then your critical p-value to have type 1 error of 5% should be 5% divided by 10, which is 0.5%.